Chapter 12 Electricity. Electricity in our daily life.
Our life is made comfortable and easy by many appliances we use. We use bulbs to light our homes. We use fans and ACs to make our summers comfortable. In winters, we use heater to keep our homes warm. What makes these appliances work? It is the electricity. Electricity plays a very important role in our life. We cannot imagine a life without electricity. Imagine you are watching an interesting cricket match on TV and suddenly electricity goes off. It will be a really annoying experience, isn't it? Electricity makes our life comfortable and easy. Thus, we can say that electricity is one of the most useful form of energy that is available to us. Let's do a quick check.
Electric current and circuit.
When water flows in a river from a higher level to a lower level, forming waves, it is called a current of water. Similarly, if we make electric charges flow by applying a force, a current of charges is created. The flow of electric charges under the action of a force constitutes electric current.
Activity. Take a torch, take out its cells and try to obtain light. Is it possible to get light? No. Can you tell why? This is because cells are the source of electricity which makes the bulb glow. Take two small copper wires and join its ends to a small bulb. Join the other two ends of the wires to a dry cell. Observe the bulb. The bulb glows. Here the electric current generated by the dry cell flows through the copper wires and hence through the bulb. The current passing through the bulb makes it glow. Take out any one end of a wire connected to the cell. Observe the bulb. The bulb does not glow since one end of the wire is disconnected from the cell. This shows that the wires should be connected between the cell and the bulb to make the bulb glow. Hence, a closed path is required for the current to flow in the wires and the bulb. The closed path through which electric current flows is called as a circuit. Let us understand what makes the electric current flow in a circuit.
Matter is composed of atoms, and every atom has protons and neutrons present inside its nucleus. While the electrons revolve around the nucleus in their fixed orbits, only electrons can move from one point to the other, unlike protons and neutrons, which are fixed inside the nucleus. In some substances, like metals, the electrons in the outermost orbit are loosely bound to the nucleus and can easily be detached from the atom. These electrons move randomly in all directions and are called free electrons. When a force is applied and these free electrons are made to flow in a particular direction, they constitute electric current. It is interesting to know that metals contain a large number of free electrons moving randomly in all directions, which are readily available to constitute electric current. Electric current is defined as the rate of flow of charges. It can also be defined as the amount of charge flowing through a conductor at a given point per unit time. If Q is the net charge flowing through any cross-section of a conductor in time t, then current I is given by I is equal to Q upon T. The SI unit of charge is coulomb and is symbolically represented as C. The SI unit of time is second. Hence, the SI unit of electric current is coulomb per second or ampere, which is named after French physicist
André Ampère.
The instrument used to measure current is called an
Ammeter.
The electric current in a conductor is said to be 1 ampere when a charge of 1 coulomb passes through a given point in 1 second. That is, 1 ampere is equal to 1 coulomb upon 1 second.
Small
Values of
currents are expressed in milliampere and microampere. 1 milliampere is equal to 10 to the power minus 3 amperes. 1 microampere is equal to 10 to the power minus 6 amperes. While large
values of
currents are expressed in kiloampere and megaampere. 1 kiloampere is equal to 10 to the power 3 amperes. 1 megaampere is equal to 10 to the power 6 amperes.
Direction of electric current. When electricity was invented, scientists were known that there are 2 types of charges: positive charges and negative charges. But during that time, electron was not discovered, and it was believed that electric current results only due to the motion of positive charges from a positively charged object to a negatively charged object. This direction of flow of charges was thus taken as the direction of electric current. Thus, the direction of conventional electric current is taken from the positive terminal of a cell to the negative terminal through an electric circuit.
drift speed of electrons. At room temperature, the free electrons in the metal wire move randomly in all the directions when no electric source like a dry cell or a battery is connected to the wire. When a source of electricity like a cell or a battery is connected between the ends of the metal wire, an electric force acts on the free electrons present in the wire, making them to move towards positive terminal of the cell or the battery. The electrons gain velocity in the direction of the electric force. This velocity gets superimposed on the random velocity of the electrons. As a result, the electrons in the conductor move with a certain average drift speed towards the positive terminal of the cell or the battery. This flow of electrons constitutes the electric current in the wire.
Let us solve some numerical problems based on the topics we have studied.
Problem 1. A current is of 0.2 ampere is flowing through a bulb for 5 minutes. Find the charge that is flowing through the circuit. Solution. Let us first write given quantities. Current I is equal to 0.2 ampere. Time T is equal to 5 minutes, which is equal to 5 into 60 seconds, which is equal to 300 seconds. We have to find total charge Q flowing through the circuit. It is given by Q is equal to I into T. Substituting given values of current I and time T, we get Q is equal to 0.2 multiplied by 300. Therefore, Q is equal to 60 coulomb. Hence, the charge flowing through the circuit is 60 coulomb. Problem 2. A charge of 420 coulombs is flowing through a circuit for 10 minutes. Find the current in the circuit. Solution. Let us write the given data. Charge Q is equal to 420 coulombs. Time T is equal to 10 minutes, which is equal to 10 multiplied by 60 seconds, which is equal to 600 seconds. Let us find the current I flowing through the circuit. It is given by I is equal to Q upon T. Therefore, I is equal to 420 divided by 600, which is equal to 0.7 ampere. Therefore, the current in the circuit is 0.7 ampere.
Problem 3. Calculate the number of electrons constituting 1 coulomb of charge. Solution. We know that the charge of an electron is 1.6 into 10 raised to minus 19 coulomb. Now, if charge is 1.6 into 10 to the power minus 19 coulomb, then number of electrons is equal to 1. So, if charge is 1 coulomb, then number of electrons is equal to 1 upon 1.6 into 10 to the power minus 19 into 1, which is equal to 10 to the power 19 divided by 1.6, which is equal to 10 divided by 1.6 into 10 to the power 18, which is equal to 6.25 into 10 to the power 18. Thus, 6.25 into 10 to the power 18 electrons taken together constitute 1 coulomb of charge. Let's do a quick check. Electric potential and potential difference. Have you ever thought What causes an electric current to flow? Let us perform an activity to understand about flow of charges and potential difference.
Activity. Take two water tanks having taps near their bottoms and label them as Tank A and Tank B respectively. Keep Tank A at a higher level than Tank B. Mix some color in the Tank A. Connect both the tanks using a transparent pipe. Turn on the tap and observe the setup carefully. What do you observe? Well, you can see the water flowing in the pipe from Tank A to Tank B. Can you explain why the water is flowing from Tank A to Tank B and not from Tank B to Tank A? Well, the water in Tank A is at a higher level, which means a point of greater potential energy than in Tank B, and water flows from a higher level to a lower level. When the water in both the tanks come to the same level, the flow of water stops. Hence, for the water to flow between the two tanks, there should exist a difference in potential between the two levels. In the same way, current flows on account of difference in electric potential between the bodies. When positive charges accumulate on a body, it is said to be at higher potential. If we connect this body to an uncharged body or a body with lower potential with a metal wire, there would be a flow of charge. Hence, there should exist a potential difference between the 2 points for an electric current to flow between them.
Electric potential at a point is the electric level at that point. If there is a difference in the electric potential at 2 points, we say that there exists an electric potential difference between these 2 points. To elaborate this concept, let us consider a copper wire connected in the form of a loop. Is there any current flowing in the wire? No. Can you guess why? This is because charges move in random directions such that there is no net transfer of any charge across the conductor. Here, all the charges are at the same potential. Now, let us connect a battery with the copper wire. The end of the copper wire connected to the positive terminal of the battery is at a higher or positive electric potential, and the end of the wire connected to the negative terminal of the battery is at lower or negative electric potential. That is, there is an electric potential difference between the two ends of the wire. Hence, a current is set up in the wire as soon as the battery is connected to the wire. In other words, the battery creates a potential difference between the ends of the loop, and as a result, a current is set up in the loop.
Electric potential difference between 2 points in an electric field is defined as the amount of work done to move a unit charge from one point to another point. Hence, potential difference V between 2 points is equal to work done W upon charge Q. That is, V is equal to W divided by Q.
Potential difference is abbreviated as PD. The SI unit of potential difference is volts, denoted as V. It is named after an Italian professor, Alessandro Volta.
Electric potential difference between 2 points in an electric field is said to be 1 volt when 1 joule work is done to move an electric charge of 1 coulomb from one point to another point. Hence, 1 volt is equal to 1 joule upon 1 coulomb. That is, 1 V is equal to 1 J upon 1 C. Small
Values of
voltages are expressed in millivolts and microvolts. 1 millivolt is equal to 10 to the power minus 3 volts. 1 microvolt is equal to 10 to the power minus 6 volts. While large
values of
voltages are expressed in kilovolts and megavolts. 1 kilovolt is equal to 10 to the power 3 volts. 1 megavolt is equal to 10 to the power 6 volts. The instrument used to measure potential difference is called a voltmeter. The voltmeter is always connected in parallel across the points between which the potential difference is to be measured. Now, let us solve a numerical based on potential difference.
numerical problem. Find the amount of work done if 3 coulomb of charge is moved through a potential difference of 9 volt. Solution. Let us first write the given data. Charge Q is equal to 3 coulomb. Potential difference PD equal to 9 volt. Let us determine the work done W using formula PD is equal to W upon Q. Therefore, W is equal to PD multiplied by Q. Substituting the given values of Q and PD, we have W is equal to 9 multiplied by 3. W is equal to 27 joule. Therefore, the work done in moving a charge of 3 coulombs through a potential difference of 9 volt is 27 joule.
Let's do a quick check. Circuit diagram and symbols used for electrical components. An electric circuit can be represented by means of a simple diagram called the circuit diagram. An electric circuit basically comprises a cell or a battery, a plug key connecting wires and electrical components. In a circuit diagram, various components of the circuit are represented by their standard symbols such as an electric cell. An electric cell provides the necessary electrical energy, that is, potential difference to a circuit. In the symbol of electric cell, the shorter line denotes the negative terminal and the longer line denotes the positive terminal. A battery. A battery is a combination of 2 or more cells which provides large potential difference to a circuit. A plug key or a switch, open. A plug key or a switch in open state allows the flow of current in a circuit, that is, it switches on the circuit. plug key or switch close. A plug key or switch in closed state stops the flow of current in a circuit, that is, it switches off the circuit. Connecting wire. A straight line represents a connecting wire between any two components of the circuit. A wire joint. A wire joint indicates that two wires are forming a junction. Wires crossing without joining. This symbol indicates that two wires are crossing each other without joining. An electric bulb. An electric bulb indicates the presence of electric supply. A resistor. It reduces the available current flowing in a circuit. A variable resistance or a rheostat. It regulates the available current in a circuit without changing the voltage source. Ammeter. An ammeter is a measuring device which measures the electric current flowing in a circuit. It is connected in series. Voltmeter. Voltmeter is also a measuring device which measures the potential difference between 2 points in an electric circuit. It is connected in parallel.